All right, let's get started. Today we're going to be talking about mature siliciclastic sedimentary environments, and again a recap. What we're doing now is we're starting to tie in the petrology to the sedimentology side of things. So our lab this week, which I believe is lab number 3, lab number 4. Okay, so lab number 4, that's the one that's due next week, is dealing with the petrology of siliciclastic sedimentary rocks, specifically mature ones, and then the second lecture of the week, we talk about some depositional environments. Okay? And the idea is to link as much as possible what we've talked about previously in terms of processes with what we're going to see in the lab in terms of rocks. All right, so when we met last time, we started talking about, what is with this thing? Computers really hate me today. We started talking a little bit about the whole concept of petrology, and these were the 4 things that we started dealing with. We talked about the major types of sedimentary rocks. We recapped important grain parameters and how they applied to what we're dealing with. And the thing to note here is that some of the parameters we're considering are associated more with energy than they are with whether a sediment is mature or not. So please try to keep those things separate when necessary. The ever difficult concept of cement versus matrix, and then of course introducing some of the sedimentary rocks and mature sediments you're going to be dealing with. So today, let's see, who are we going to choose to look at this today? Who's looking like they are not entirely falling asleep right now? Daniel? You've been working on structural geology. Leave that beside now and talk us through this. These are the major sedimentary rock types. And?
The siliciclastic rocks are the most common, and they're mostly made of silicates, especially with quartz in our area.
Exactly.
Volcaniclastic are usually volcanic rocks that are formed in a sedimentary-like fashion, like tuffs.
That's good. Now that's a very good point to make, that they are volcanic rocks, but they're volcanic rocks that are more or less deposited as sediment, hence the term volcaniclastic. And lastly?
And carbonates are evaporite chemical deposits like limestones.
And of those, which are by far the best ones, the ones that I find most interesting? This is how you get your A, dude. Which one is it?
Carbonates.
Yeah, the carbonates. And as you see when we get into them, I like them because they overlap so many different areas, as well as having that diagenesis history to them, where you can actually look at how things have changed in the past. What about this? This is our dreaded QFR diagram, and what does the concept of mature actually mean?
It means that it's been transported a long distance. Erosion has happened a lot, so most of the feldspars and other rock fragments have been eroded away.
Or weathered away, and it has to do with chemical stability, correct?
Yes.
That, as you should be aware, different minerals are stable to different degrees at the surface of the Earth, and around here, quartz is just about the most stable thing we have. Now, just a point of clarification, I'm not sure if someone said this or if I just heard you say this last week, or whether I'm imagining entirely, but some people comment on the idea that heavy minerals are also unstable. As it turns out, many heavy minerals are even more stable than quartz is. Things like magnetite, the garnets, ilmenite, those things can concentrate to a certain degree in very mature environments such as beaches, which is the reason why you sometimes get black sand beaches and also. Now, let's talk a little bit about some of the parameters. Grain rounding. What does grain rounding actually be induced by? What's causing this?
The movement of water over the sediments, so that as water passes through, as the sediment gets more mature, the grain size becomes more rounded.
Not the grain size, but the grain shape. And this is a pretty good linkage, that the more mature sediment is, in general, the more weathering it's undergone and the more transport it has undergone. And while down here, most of the transport we see of sediments is via water, specifically flowing water, in some environments, for example, desert environments where there's very little water, you can get significant amount of rounding being done by the blowing wind. In fact, there's a sandblasting effect. You may be interested to know that the differences between whether something's been sandblasted by air or water washed is very easily discernible using a scanning electron microscope. Water tends to polish the grains, whereas wind tends to abrade them, and you get these little sand pits on the edge of it. And under a scanning electron microscope, it's very, very obvious. Now, grain sorting is controlled by what?
Energy of the liquid that's passing over.
right? Not again even the liquid, but the energy of deposition. So as a general rule, if you have a lot of energy and it's consistent, the sorting should be better than something where there is kind of inconsistent energy. And of course, the most poorly sorted sediment of all, anyone know what it's associated with? Glacial till. Yeah, the idea of just having a bulldozer moving stuff, there's no sorting whatsoever. And of course, that's one of the greatest means by which of identifying glaciations in the rock record is by looking at the presence of these really, really incredibly unsorted sediments. And grain size is also related to?
The energy.
To energy. And this is probably the most misleading of the slides we saw the other day. The idea that higher energy is going to give you greater size sediments than lower energy is more or less true. But I think we also have to add on here the idea it's consistent energy. If you have a very well sorted sediment, whatever the energy was associated with it had to be consistent. If it was inconsistent, you're going to get a mixture of grain sizes. So a very well sorted, very fine sand and a very well sorted coarse sand, different energy levels obviously, but consistent for both of those. Okay. Then we start talking about petrography, and again, here's where you're going to have to play a little bit of catch-up. You've all had a chance to look under the microscope in at least one course prior to this, and if you're taking petrology now, you're going to start seeing some things under the microscope fairly soon as well. The idea now is that the microscope gives us another level in which we can actually identify sedimentary rocks. So this is a picture of a cartoon image of what a mature sedimentary rock might look like, a mature siliciclastic sedimentary rock might look at under XN. What does XN mean again? Cross polars or cross nickels. The idea now that you have the bottom polarizer in, which is standard, that's plain polarized light, and then you put the top polarizer in. And a reminder, the bottom polarizer has a grid that's like this. The top one is perpendicular to it. And if there wasn't a material capable of affecting the path of light, if the material that you were looking at was isotropic, say glass or air, then when you cross the polars, of course, everything goes black and stays black because you've stopped all the light vibrations. But when you start putting anisotropic minerals beneath the top polarizer or between the two polarizers, then it can start to change the vibration direction of the light, and that can allow some light to come through, and that's where we get this wonderful diagnostic ability to identify what grains are. Now, as far as I can tell, of the 24 people that are in this class, a whopping 2 of you actually were in the lab last week or last Tuesday looking at thin sections. So for the 2 people that were in there, did it come back to you a little bit? All right, so again, this is going to take a little bit of time. You know, last time you looked at a microscope might have been, in some cases, over a year ago. So it's going to take a little bit of time getting used to it. So put as much time into the lab as you possibly can, okay? And I will provide you additional pointers, things that I didn't have a chance to do in mineralogy, or probably David Allison didn't have a chance to do in petrology either, to get you to learn to identify more grains. Anyway, in terms of this particular image, the mature rocks are largely going to be composed of quartz-rich sediments, so they're going to be coarse aaronites. The grains will be generally well-rounded because long transfer distance, and the sorting and grain size is going to be dependent upon what you're dealing with. And of course, the majority of all these grains in this field of view would be quartz, right? All right. And what is the property where the grains have different colors under cross polars called again? Birefringence. Anybody remember what the property is where a grain, not all of them, but some grains will change their color upon rotation under plain polarized light? Congratulations! How many of you remember it was pleochroism? Maybe things haven't all sunk out. Maybe Mardi Gras doesn't sap your brains out entirely. I thought it might, but perhaps it doesn't. Oh, and I know what it is. None of you have watched Breaking Dawn for a while, have you? Because if you watch Breaking Dawn, the Twilight episode, it will, I guarantee it will suck your brain dry. I'm still recovering from that. All right, and then we came to this, which was the dreaded matrix versus cement. Now, what is matrix again, Daniel?
It is sediment that's deposited exactly at the same time as the other sediment.
And that compares with cement?
Cement is the chemical process that comes in after.
And the key thing here is timing. Matrix is deposited simultaneously with the coarser grains that make up the sandstones or whatever rocks you're looking at. Cement comes in later. And as I tried to caution you, the way I've written this up here, it says that cement comes in long after the deposition is over. That is sometimes true. There are cements that might not start to form until many tens of millions of years after deposition was terminated. But there are some cements that can form really, really quickly. And indeed, when you went on your honeymoon, and I was asking you, did you see beach rock? Beach rock, if you're not familiar with it, is a rock that forms on the beach. What happens is, when the tides come in and the water comes in, there's just enough chemical materials in the water to induce cementation. That's actually happening while the stuff is on the beach. That's pretty well almost the same time as deposition is taking place. But it still is a secondary process. And of course, these are the different processes. You don't have to worry about reading these things off. These are the ways you can tell the difference between matrix and cement in thin section. And again, you should think that this would be the easiest thing in the world to do. I mean, look how different they are from one another. But consider that some of the cements may actually look very much like matrix. In fact, one of the more common cements that we have in this part of the world is, in fact, a clay cement. And clays are the same type of thing that make up the majority of matrix as well. So when you start having cements and matrix composed of the same materials, things get a little bit more dodgy, okay? And as I said, some of the thin sections we have are really very good at showing you good clay cements. And if someone sees something they don't understand, flag me down. If it looks really cool, or if it's something that everybody should see, I will tell everybody to come and take a look at that particular image. And that there isn't a year that goes by that we don't spend a few minutes in every lab looking at other people's thin sections. These are some of the thin sections you're going to be looking at, and I encourage you, when you get your samples, don't go looking for a specific sample unless I ask you to do so. Grab one, then look for an accompanying hand specimen. Check the documentation for each of the labs, because in some cases I'll say substitute certain specimens for certain thin sections. And those of you that have access to labs or lab books from last year, and I know they're out there, do yourself a big favor. Use them as a guide, but do not use them to provide the information that I'm asking you to look for. Because remember, this is a learning exercise. Look at the thin sections, learn how to identify the minerals that are in there, learn how to be good sedimentary petrographers. Otherwise, you're doing yourself a big disservice. And lastly, this is the type of thing you're going to be seeing. And I was very happy to see that both of you had a chance to look at this thin section, right? All right, so the blue that you see here is, of course, porosity. Anything that's not stained blue is usually going to be a mineral of some sort. But put it through the normal test you would do for any type of thin section. All right, thank you, Daniel. That was well done. Today what we're going to do is talk about, as I said, a mature depositional environment. You guys are pretty familiar with this. And I really like talking about these rocks as being our introduction to how petrology works. Because I can mention things about beaches to you. You can close your eyes and you can transport yourself down to the beach. Because we live along some of the best beaches anywhere in the world. Once we get into more abstract environments, at least as far as we're concerned, then you have to sit down and think a little bit more about them. You have to understand more about the processes. But here it's really quite nice to talk about beaches, because I can tell you the factors that influence beach development, and we can compare really good beaches with our beaches. In some cases our beaches are excellent, in some cases they are not so good, at least as far as the geology is concerned. Then we talk a little bit about beach profiles, and ultimately the facies associated with beaches and some of the sedimentary sections that you might expect to see along here. And the idea for doing this is to introduce you as to what type of thing is going to be deposited in the rock record, so that a little bit later on, if you happen to be somewhere working as a sedimentologist or a geologist and you come across a sequence that has got variables, facies in it that get you thinking about processes that might be occurring at the beach, then you'll be able to make the linkages to what you're seeing to what was occurring when those sediments were first being deposited. All right, let's first of all talk about factors controlling beach development. Now, these are the most important ones, okay? Number one, you need to have a steady supply of sand to the shoreline. And the sand can come in through a number of traditional ways: by river, by delta, or by longshore drift. Along our parts, sometimes the sand is coming in by a dump truck. If you think about it, you'll understand what that's all about. The idea is sand-sized sediment must get to the shoreline. Now, where we live, we actually have some major rivers flowing into our coastline. But given the nature of our coastline, very few of those rivers are actually responsible for bringing a lot of sand to our shoreline. The Mobile River is a classic example. Where's all the sand from the Mobile River being deposited? Not even the west side of Mobile Bay. Where's it being deposited?
In the channel.
Not quite the channel. It's actually being deposited at the head of Mobile Bay. The rivers transport sediment in confined flow, like a flume. But the minute you get into a standing body of water, and Mobile Bay is a standing body of water, the coarse-grained sediment is deposited. Every time you drive over the Bayway and the tides are down, look around you. I've been here for 20 years, and the amount of sand that's been deposited in there is incredible, because it's being deposited at the head of Mobile Bay. And indeed, we refer to that as a Bay Head Delta. It's the best one I know of anywhere in the world, and nobody studies it. When you get down to the end of Mobile Bay, there's no sand really coming out anymore. What's coming out at the end of Mobile Bay? The finer stuff. And fine stuff does not make good beaches. So that begs the question, where did the sand from Dolphin Island come from? Maybe you don't know your beaches well enough after all.
It should be coming from longshore drift.
It is coming from longshore drift, which means it's got to be coming from the direction in which the longshore drift is coming from, which is Florida. And ultimately, the river providing most of the sand for our beaches from Florida all the way out to probably, well, Biloxi doesn't have natural beaches either. Florida, to where we are, is ultimately coming from the Apalachicola River. Okay? So we get a steady supply of sand, but in some cases it's going to be very spotty in terms of where it comes from. You need to have a wave-dominated setting. Good beaches require the swash associated with waves breaking along the shoreline. Ideally, you want medium to high energy waves. Low tidal energy is also necessary. Now, we live in an area where there are incredibly low tides. How would you deem our wave energy around here? Pretty darn low. And in fact, if you look on paper, the combination of low tidal energy, which is good for beaches, and low wave energy, which is bad for beaches, would kind of give you the idea that we're not going to get a lot of really good beach development here. And indeed, in some cases, we don't. The beaches we have here, as good as they are relatively thin ribbons attached to, in some cases, much more muddier types of environments. The best beaches in the world, no offense to Pensacola, in terms of beach processes, are going to be in areas where the waves are tremendously high, like Hawaii, or the east coast of South Africa, or most of Australia. Anywhere where people surf is a good place for dealing with beaches, because the surf is associated with big waves. And lastly, this is one thing that we do satisfy quite nicely. You need to have a stable, very low gradient coastal plain and a fairly wide shelf as well, okay? So that what you want to have is an area where the waves can build up and pile up. And indeed, that's what we have here. Now these are, if you look at this is fairly restrictive in terms of where good beaches could form. But when you add them all up, this thing is really not working. What's going on? Something is not quite right. When you add up all the requirements and look at the planet as a whole, you still find that we have an incredible amount of potential excellent beach footage around the world. Some 32,000 kilometers of shoreline meet the bill for having excellent beach development. Just beware. If you have rivers that tend to be depositing more fine-grained material, for example, the Mobile River as it gets out past Mobile Bay, actually it's not even a river by that time, where Mobile Bay comes out, or the Amazon River produces a tremendous amount of mud because of the intense tropical weathering regime that it's draining. So you don't get really good beaches in environments like that. Instead, you get muddy types of shorelines, and we're going to exclude those for the rest of our discussion. We're just going to be talking about beaches that involve sand, and we do get some really good ones along the U.S. eastern coastline as well as the Gulf Coast. Now, here's how it all works. We're talking about wave energy now, and we've already had an introduction to how water moves. Wave energy is associated with orbicular motion, the idea that the waves are being driven by the wind. And you don't need much wind. 3-mile-an-hour wind is sufficient to throw the water into waves. But the stronger the wind, the more the orbitals can affect the environment. Okay, so the idea now is when the wind starts to blow, the top part of the ocean water tends to be thrown into these big orbitals, like so. Okay, so here's an explanation for what you're going to get. The idea now is that water molecules will follow this type of motion as the waves come by and go past it. It stands to reason that since this is a wind-generated phenomenon, that the deeper you go, the less influence the wind is going to have in the water, the orbitals start to close up. As these orbitals start to move in this direction, because of interactions with the seafloor, you'll start to cause the orbitals to start to tip over. This gives rise to a buildup process. Eventually the waves will break, and then it will convert the motion from orbicular motion to more or less a forward motion. So you go from orbicular to a back and forth motion through here, okay? This diagram is critical for understanding how the orbitals, the water movement, the substrate, and the change of water movement occurs. In deep water environments, okay, so here's an orbital now, highest at the surface, decreasing in size as you go deeper and deeper. Eventually you pass below what we call the wave base. This is below the level in which water will be moving courtesy of the wind. All right, so this is a plane designated by or delineated by the depth of these orbitals. As you get into shallower and shallower water, the wave base will start to intersect the seafloor. And instead of there being no motion below the wave base, now what will happen is these orbitals start moving back and forth in a back and forth motion because of the influence of the waves. And of course, as you get into shallower and shallower water, that becomes more extreme in terms of its overall motion. All right, so the idea is that this motion, orbicular, eventually starts to do this and then becomes more pronounced. And it's this motion, which can be actually quite rapid, that gives rise to predictable sedimentary structures like upper plan lamination. Now, this diagram is a very busy diagram. I believe you've seen it before when we were talking about something earlier in this course. But what it does is it relates a lot of this movement component of water to the types or morphological features that you might expect to see on the beach. So once again, here is our orbitals. And by the way, one of the easiest relationships in science, mathematical relationships, is the depth of the wave base, which can be determined based upon the wavelength of the waves divided by 2. That gives you approximately the bottom of the wave base. Depending upon how big the waves are, the wave base can be anywhere from a couple inches, literally, to maybe 15 meters or so. Okay, so remember, this is a diagram that's generic for all environments. And if you're dealing with a really good beachy environment where you are going to have very strong waves where you can surf, then of course the wave base is going to be deeper than this. Every once in a while, and our coastline is perfectly suited for this, you're going to have storm events that will make the waves bigger. It's the only time you can go surfing south of Mobile is when there's a hurricane off the shore. When you get bigger waves, that depresses the wave base, and we go from what we affectionately call the fair weather wave base down to the storm wave base. In some cases, the storm wave base can be 100 meters below the surface. That will, of course, change the dynamics of everything. The constant movement of water, the constant transition from going from orbicular motion to the swash motion is what ultimately develops things like longshore bars, the surf zone, and all the morphology that characterizes what we like to call healthy beaches. Also on this diagram, and again, you have to understand that when you're dealing with environments, understanding modern environments is one thing, but also being able to look at this as to interpreting things in the past, you want to have as much information as possible. So down here along the bottom, you're actually seeing different intervals of certain trace fossils. We don't focus in on trace fossils in our program at all. Some schools that have, say, fairly large graduate programs will have an ichnologist, and that person will be responsible for identifying trace fossils and studying trace fossils. They get excited by this type of distribution of things. Now, as well as dealing with the idea of wave motion pushing water into it, you also have to realize, too, that when you have a very shallow gradient, what often happens is water can pool on top of your environment. This is particularly true if the waves are coming in faster than the water can return back due to normal draining processes. So in a situation like this, you can have different types of currents being developed. Longshore currents occur when the wind is blowing obliquely to the shoreline. What happens is the waves will move in this direction, and then when the water returns back, it flows down gradient. The next wave comes in like so. Next thing you know, there's a residual current moving along shore, in some cases taking sediment along with it. And longshore drift, that movement of sediment along the longshore current, is the reason why we're getting sand replacing the sand on our beaches here. You can also have developments of rip currents or undertows, and I don't think anybody who lives along the Gulf Coast needs to be told about this. Your mother was warning you this the minute you started walking in the water all by yourself. What do you do if you experience a rip tide or rip current? Yes. The idea now is what happens is water is pooling here. You can actually have a higher amount of water pooled up in one spot. Eventually what will happen is it will force a current to flow perpendicular to it, and if you get caught up in that, then it's going to take you for a ride up until the point that the water disperses, and then it could be in some cases many miles offshore. Not where we live, but certainly along some parts of the world where you do have very big waves. You would not want to get caught up in a rip current unless you knew how to deal with it, because you may never be seen again. Okay, so now let's link this to current movement to things like bed forms. We've already talked a little bit about how if you start having currents, you're going to get bed forms. And even if you don't have unidirectional currents, you can still get bed forms like wave ripples forming. So consider now, here again is how our waves are building up. There is the standard orbicular flow. The waves start to build up. The minute wave base intersects the seafloor, you start to slow down the waves. They start to tip up, grow bigger, and eventually what will happen is the waves will start to break. Now, breaking occurs as you start to compress the water waves. They build up, and there's only so high a water wave can build up. Most waves might look like this, but as they're building up, they're getting steeper and steeper and steeper. The fact that the bottom of the orbitals are intersecting the seafloor also causes the bottom to drag a little bit. Next thing you know, you're tipping the waves over, and then they will break. Now again, the ideal breaking is the type of thing that you would see on episodes of Hawaii Five-0, where you see this big wave curling, and then there's a surfer going right down. What do they call it? Shooting the tube? All right, that's a breaking wave. And this normally takes place offshore, and then the water surges in, giving you this back and forth motion. So as you go offshore, or as you start off in deeper water and move inshore, you're going to start to see the bottom of the seafloor reflecting the type of currents that are affecting it, given what the waves are doing. During fair weather processes, when you first start to get to the bottom where the waves are intersecting, you'll start seeing wave ripples forming. As you get into shallower and shallower water, you're going to get current ripples, possibly, or certainly large ripples anyway, because more water is moving. And as you get further and further inshore, including onto the swash zone and through here, these are going to be areas where the depositional conditions are so high energy that the only thing that's going to be able to survive here is going to be flat upper plan lamination. Now, we talked a little bit about this particular type of structure too, because the surface itself is not flat. You have an inclination here because you're coming out of the water, so you get parallel lamination sitting on top of an inclined surface, which leads ultimately to something like lower plan lamination. And of course, when things get stormy, everything changes because all these bed forms can shift further offshore. I like this diagram because it allows us to link now some of the hydrodynamics, and the hydrodynamics is how water moves, with some of the sedimentary facies and morphologies. And most people here that live in this area are more familiar with this concept because we've walked along beaches. The one disadvantage we have living along the Gulf Coast is that our beaches are anything but healthy. We've talked about the idea that our sand comes from the Apalachicola River. We've talked about our sand coming in from longshore drift. We should have also addressed one little complication. If there's any interruption to the longshore drift, then you're not going to get sand being added to the various types of beaches. And we have one pretty prominent interruption called the Mobile Shipping Channel. Every couple of years, the Army Corps of Engineers has to go in and dredge out the channel, which for some reason seems to keep getting filled up with sediment. That, of course, is the sand that's coming in from Florida. And unfortunately, what they do with that sediment is they take it further offshore and dump it, so it's not going to be a problem with the shipping channel anymore. Net result is there isn't a steady supply of sand replacing the sand that is continuing to take sand further west courtesy of longshore currents. And this is why Dauphin Island constantly has to be nurtured. New sand is added all the time, and they start having to build up riprap structures to protect whatever structures happen to be out there. It's not a particularly good situation, okay? If we lived along a good beach, however, this is the type of thing that we might expect to see. We would see dunes. Dunes are caused by the wind blowing sand laterally. Then we would find these two little flat depositional surfaces. Some people call them berms, some people call them terraces. One is associated with the high tide, one is associated with the low tide. When you live along an area where there's very low tidal range, those two flat surfaces can merge into one another. In fact, sometimes they look a little bit inclined, okay? And then as you go offshore, there's a bit of a scarp face, and then you'll start seeing some longshore bars and some longshore troughs. Now this is a stable beach. And the idea here is that the constant working of the water back and forth tends to flatten out things right along where the swash is, upper plan lamination, very well sorted sediment in this area. And because you end up having the sand being transferred back and forth, getting longshore bars where breaking normally takes place also allows to have these types of morphological features being developed. Fortunately, where we live, because we are living in an area where there's not enough sand coming in to replenish the sand being removed, we're getting erosion more or less taking this all out. And I can't remember the last time I saw a good dune on Dauphin Island that was not constructed artificially. It's unfortunately somewhat true to see these types of issues on the eastern shore as well. It's a more stable beach. There's more sand being moved along there. But there we have the problem of an awful lot of development. And developments on beaches also change things quite a bit. Anybody who builds a jetty on the beach, for example, should be shot. In fact, in some cases they are. Maybe not in this country, but you start screwing up the distribution of sand and all sorts of bad things happen. Okay? So each one of these morphological features is going to have unique sedimentary structures, unique sedimentary criteria, hence we can designate specific facies for them. Now from a larger picture, we should probably start talking about beaches in general, because I haven't really talked to you about the different types of beaches, and like every other sedimentary environment that we're going to be dealing with, there are versions and many different versions of each environment. So yeah, we may be talking about beaches, but you have to understand that there are a bunch of different beaches according to the nature of the sand and how it's being deposited. This is a lovely cross-section, again, another one of Roger Walker's diagrams that very quickly summarizes the major morphological features, the major sedimentary facies associated in this case with a barrier island complex. Barrier islands are designated as very large depositional features that are islands. You have sand being deposited somewhat offshore from the mainland. Between the island itself and the mainland is some sort of a lagoonal feature. And these are things that are very characteristic and very typical of the U.S. Gulf Coast, probably more so here than anywhere else in the world. And I think you can recognize some of the environments we have. There's Dauphin Island, there's the mainland, these are all the mud flats. I wouldn't exactly call them tidal flats because our tidal range is so low here. The vegetation covered things that surround the coastline between the mainland and Dauphin Island. The neat thing about barrier islands is that they may be beaches, but they're beach complexes. On one side, where they label the beach here, I call that the open side of Dauphin Island. It's the side that's open to all the wave energy. If you go to Dauphin Island today and stand where Sand Island is docking, where the old pier is, what you're looking at is the area where the full brunt of all the energy of our waves hits, which around here is kind of like that. If you go to the opposite side, which is the sheltered side, that's an area where the wave energy, regardless of whether we lived in a high wave energy environment or not, would have been greatly reduced because it's on the back side of the island. In these environments, this is normally where you get the finer grained stuff being deposited. And again, where we live, where Mobile Bay has sediment being dumped out from the ultimately Mobile River, but it's all mud. That fine-grained stuff can form very large mud deposits behind Dauphin Island, which they do. And when you go over the bridge, what you'll see are deposits that are largely muddy, and vegetation loves those things. That's why you end up seeing all these vegetated flats on the backside. Okay, the lagoon itself is going to be mud dominated, and the surrounding areas where marshes are going to be mud dominated as well. Wherever you happen to have channels, and we have a very large channel between Dauphin Island and Fort Morgan Peninsula, and every once in a while Dauphin Island will be cut. And by the way, when that happens, it normally takes out a house or two. There are places you don't want to build, and a barrier island in an area that's prone to hurricanes is definitely one of them. But when you start having a channel, even though the tides are minimal now, when the water comes up a foot and you have a narrow channel, that equivalent water passes through the channel remarkably fast, starts to erode sediment, creating a fairly deep inlet, and then when it gets to the other side and branches out, the currents slow down, you deposit sediment. You end up getting what are called tidal deltas, one associated with the flood event, where water's coming in, and one when the water's returning, called the ebb tidal delta. Those things are cool. But I pity anybody who happens to live in an area where a river or where the tides want to cut through an island. And we've seen this several times here along the Gulf Coast and along the US eastern seaboard as well. Someone buys property, a hurricane comes through, their house is destroyed, a tidal inlet opens up because that's where the water was pushed through, and then we have this problem. What do you do when you bought property which is now gone because basically the water surged through it? There's some incredible images that have been done over the years. When Hurricane Hugo took out a bunch of the barrier islands in North Carolina, after the storm was over, the people who owned the property went to the insurance companies and said, my house is gone, my land is gone, I want it back. So they came in and started putting sand back in. One image I saw was a bulldozer moving sand in. Well, once a tidal inlet opens up, the water moving back and forth through it, it takes a lot to slow that down. 2 weeks later, there were 4 bulldozers, all bulldozing like crazy, trying to stop the water before it could wash away the sand. After a couple weeks of hard efforts, they managed to win. They blocked the channel and they built a new house on top of it. What's going to happen the next time a hurricane comes through that area again? All right, so you see the issue here now is that looking at modern processes now are interfered with by the very presence of humans there causing things to change. This is a healthy system, and you'd expect to see sand moving back and forth. This is the way it is. Now let's talk about different types of beaches too, because as I said, we live along a place where we have one type of beach, or 2 types of beaches here, and they're good beaches, but it's not the only ones we have. This is a little cartoon section showing you different types of beaches. The first one here is typical of what we would have along parts of Florida. It's a mainland attached beach. What it is a thin strip of sand that is attached to the shoreline. So new sand is being added and processed as a narrow strip. Many of our beaches qualify as this. If you can park at a parking lot, walk across the dunes and get to the beach and see your car from the beach, it's a very narrow strip of sand. But there's some place in the world where you have these really incredibly long and wide strand plains. The eastern seaboard of the United States has many of these things, and the longest or the widest beach I've ever seen was in New Zealand. They call it 90 Mile Beach. It was about a mile from where you parked to where you got to the water, and what you did was you walked over ridge after ridge after ridge. A situation like this, what you end up having is just sand being added and building outwards. Then we have the barrier island complexes. Some can be regressive, some can be ultimately erosive. Okay, so the idea is that they're going to be coming and going overall. The one thing you want to get from all beach processes is understanding that when you're dealing with a beach, there's always a battle going on between constructive and destructive forces, or if you wish, depositing and eroding, depositional versus erosional events. Sand does not stay put on a beach. It is constantly moving. I'll wait for Dr. Allison's class. I'm sure you all would like that when structural geology is on, okay? All right, so it's constantly changing. And again, looking back at how humans interpret change like that, if you own property on a beach, you don't want things to change. You don't want things to change in your backyard. But you have to understand that there's no sand grain on a beach that is staying there permanently. It's always on its way somewhere else. And any interruption to the sand flow is going to cause changes overall, okay? So progradation and retreating are important components of what goes on in beaches. Oops. There's a delay in what's going on here, okay? I want to show you a good beach, Galveston Island. I've never been to Galveston Island. Has anybody ever been to Galveston, Texas? They tell me it's nice. It's not nice, or it's awful? Well, they tell me outside of Galveston it's nice. The island itself has nice areas to it. Galveston, the city, may not be all that cool and all. The thing about Galveston Island is that it's a very large barrier island, and one that's been studied really quite extensively. This is a very greatly exaggerated diagram across Galveston Island showing you the lagoon and the more or less how everything's built up. You can see this very big bump up to here. This is the dunes associated with things. And it gives you an idea of just how long that island has been there. Gentlemen? Sorry, did you want to comment on Galveston or something?
Yes, I was asking Patrick what kind of beach it was. He said it was really dirty.
Well, again, see, you're spoiled. A dirty beach is one that just has finer grained material on it. There are some beaches that have a lot of black sand on them because of heavy minerals. Our beaches along here are well known for being really clean because it's quartz sand. And of course, not that long ago, people were having all sorts of hissy fits over the idea that four-wheel drives might bring in red clay onto Dolphin Island and turn the beaches into something that's disgusting.
Specifically with our beaches, don't we have a relatively powerful longshore current that's transporting the material westbound?
Indeed we are. That's why Dolphin Island's as long as it is.
Yeah, because I mean on the map, everything, they just look like little wisps. So, but compared to the tides and everything,
yeah, and that's what's transferring the sand from the source of input, which is Apalachicola River, to where we are now. But there are many sources of interruptions between that, which is one of the reasons why the sand that's coming into Dolphin Island is being moved laterally faster than it's being replaced, which is why when you go to the eastern side of Dolphin Island, it's so intensely impacted. In which case we have to continue to add sand to replace the stuff not coming in. It would be a lot easier if we just replace the sand that the Corps of Engineers is currently transporting 80 miles further south. This policy. Yes?
Aren't the black sand beaches, those are in California, right?
Oh, there's black sand beaches in many places around the world. Some are being mined because that black sand, if it's ilmenite is a source of titanium. And so you can actually mine some of these beaches. In Africa, they do a lot of.
Go like play on?
Can you what?
The little sand castles.
Well, you can't. It's weird because you were saying the beaches were dirty. One of the black sand beaches I was on in New Zealand, you walk onto it, it looks like someone spilled oil all over the beach.
I bet that's burning the pot.
Not in New Zealand. At least when I'm there, it's always raining when I'm in New Zealand, so it's not an issue there. But it looks initially like you're standing on tar, and you'll see people who haven't been to this type of beach before. They'll walk and they'll look at the bottom of their feet to see if there's tar on the, and there isn't. It's because it's minerals. In fact, I think if you put a magnet over it, probably half of it would stick on there. So, and it's mineable, but the locals did not want to make it mining because, of course, then you start destroying the beach. All right, just quickly now, let's just look at some of the beaches. I don't want to go into a lot of detail about this because, we already talked about beaches when we were dealing with the discussion of fascies anyway, so this is a little bit of recap right now. But again, here's the morphological features along a pretty good beach. This one could be a barrier island cross-section or it could be a mainland attached beach. The dunes here are the dunes you would typically associate with aeolian processes, wind-blown processes. Okay, so these are the mega ripples, the large current ripples that are going to be reflecting the direction that wind is blowing on the beach, sometimes 90 degrees removed from the current directions. As you get from the dunes down to the beach proper, you're going to run across the berms, the flat part. There will be, as I said, one or two of them associated with how high the tides are. Sometimes you'll see some smaller dunes on the uppermost berm. Some people call these the primary dunes. The primary dunes are associated with water, associated with storms. So when big storms come into an area, what will happen is the water is pushing much further inshore than it normally would, and that back and forth swash motion can pile up a bunch of ultimately crap. Driftwood, stuff floating around, bigger chunks of material, the occasional dead body, etc. gets piled up in that, okay? So these dunes are wind blown. they're kind of operating independently from the primary dunes, which are the highest waves, and then we go back to the idea of the longshore bars where sediment's moving back and forth, etc. And once again, remember, each one of these components ultimately represents a facies within the beach. If you're dealing with a mainland attached beach, then what you'll see are just those facies associated with water moving back and forth and wind blowing. If this were a barrier island complex, you'd also have to factor in some of the quiet water environments, this more or less the sheltered side of things. So you see a lot of muddy deposits, perhaps a lot of roots growing, because a lot of roots growing in quiet water will leave behind organic material as well. Okay? And then ultimately, when it comes time to looking at the vertical successions of things, remember, any lateral variation of facies can be expressed in a vertical fashion, Walter's law, provided that there are no depositional breaks. So in this case, what you're looking at is a sequence of sedimentary rocks. I have no idea how old this is. That shows you the type of relationships you might see in a beachy type of environment. At the bottom here, you see the upper part of the shore face, where you see these large crossbeds. Some of them might be multi-directional because waves coming in and going back and forth. Then we get to the actual part of the beach associated with the swash. In this case, they call it the foreshore, where you have parallel upper plan bedding associated with the water moving back and forth. This is also where you'd expect to see low-angle cross-stratification. When you get towards the back side of things, where the dunes are, the sand here is largely going to be blown by the wind. Sometimes you get heavy mineral concentrations. Sometimes you get disturbances here by things that are burrowers. Crabs, for example, can burrow well into the dunes. Often you see plants up here as well, rootlets, etc. And then, of course, in many beaches, and Dauphin Island is classic for this, when you get between the dunes, you can actually have standing water where you can actually have marshy type of growth taking place. In some cases, it's not unusual to get coals. Of course, we're not going to get coals on Dauphin Island. These beds are too thin. But if you have a big enough beach where those water bodies have been around long enough, peaty type layers can in fact occur. Now, every once in a while around here, with the erosion being what it is, we get undermining of earlier beach facies. And not that long ago, we had several students working on some peat beds. Well, they weren't quite peats, but they were really organic, rich clay beds that were being eroded on Fort Morgan Peninsula in the surf zone. What was happening was the sand was being washed away, and underneath you could actually see what clearly was an organic, rich mud bed. We find similar things like that on Dauphin Island periodically, where you get soil profiles being eroded as we undermine more and more of the island. Sometimes trees are eroded out of there as well. Because what you're doing is you're exposing earlier phases of beach development. How old those things are is dependent upon when those processes took place. The Dauphin Island trees that were exposed were 200 years old. The peat bed that we found on Fort Morgan Peninsula, 2,000 years old. Okay, and that was probably forming between dunes long before humans were building condominiums on that beach. Long before we started damming rivers, while sand was more continuously being deposited back and forth. It's kind of cool stuff. And of course, you've seen this diagram before when we were talking about facies again. Here it is the identification of the specific components, how they are related in an upward direction that allows you to identify what kind of overall beach you're getting. The ability to decide whether it's associated with transgressions or regressions is associated with the vertical arrangement of facies. And if you're dealing with a barrier island, you'd expect to see things like channels and washover fans. These are things that involve water moving across the island. Things like that would be different in another type of mainland attached beach. Okay?